Hello everyone, welcome to join the talk. This is Ronaldo. I am a senior software engineer working in ACRD DMG. Today, I am very glad to have the chance to talk with my team about the Git version control system. In this session, we are going to not only dive into how to use Git, but also focusing more on how Git works from bottom to up. As we all know, Git is very popular among open source development. We must wonder why it is so hard. To get the answer, the best way is to use a tool. And if you would really like to use a tool, perhaps the best way is to dig out the story behind the tool. Let's start from some basic concepts, which seems a little bit trivial and unimportant. You may even lose patience since you don't see the connection between Git and these concepts. But believe in me, it is a must. As long as you master those basic concepts, you will soon unveil the mystery of Git. Otherwise, you will never know its true colors. Now, let's start from the very beginning. Here are some terms that you will meet when using Git. We will go into very details about each of them in the next few hours. Ideally, you should get familiar with all these terms after the session. You can go back to this page to see if you really know each of them. Yes, they are very trivial. But connect them together will finally bring with you core knowledge of Git. It's confusing how Git manages files among different versions. To understand the file system Git uses is helpful to resolve the confusion. Let's make an example. If we are now working on the Windows system, and I have created a folder named Maya, which is the root project directory. Under this directory, we have three folders named 3p, cmake, code, and we also have a file named readme.md. This is the very familiar file system we usually work on Windows system. We call this working directory since it's the real working place where we add, remove, modify files and directories. Obviously, the working directory owns a tree hierarchy since we have folders and files. I believe you are careful enough to get notice of the .git directory. By default, this directory is hidden by Windows system. But if you show the hidden files, you can simply find it under the root project folder. This is the real place where Git uses to store all objects among different versions, and it's the so-called Git repository. Git maintains each file as a blob and saves them into this repository. To conclude, we have working directory where we really works, and we have Git repository where we really saved and track history. Now, let's using Git bash to make a demo according to what we've talked just now. First, you need to initialize the Git repository. Here, we make Maya as our root directory. Simply type in git init will help you initialize the repository. Now we can see the .git folder. And then we make three folders. Also, write a new file named readme.md. We write down initialize Maya developed environment into this file. Now we will go into details about the Git repository. The file system owns a flat hierarchy. Each file saved in the repository is named by its SHA-1 code. No worry about the SHA-1 code. We will explain it later. Let's using git bash to see what happens to the repository when we make a new version. In the right panel is the command we use, and in the left top is the file explorer. In the left bottom is the hierarchy. We mark the working directory in blue, whereas the Git repository in orange. First, let's change directory into .git. We find a folder named objects. This is where we store all the history. Continue, we go into the objects folder, and we find nothing but an info folder and pack folder. Then we step into our working directory. We use git add dot to add files into the repository, and we can find two new folders named 04 and 85. We use git commit -m to commit the change, and we can find a new folder named 33. Using ls command to list the info. So now we can find that there are 3 new folders added. What on earth are these strange numbers? What are these added 04, 33, 85? Let's first use ls command to see what's in the folders. Well, even more frustrated and strange file names appear. We can find a file named by 38 digital hex code under each folder. To be simple, we will read the first 6 digits as the file name later. Till now, we still don't know the content of each file. However, we can use the git built-in command cat-file-p to check the content of each file. At first glance, we see some description in file 332703 and A56072. And to our surprise, in file 04748b, the content is what we wrote in the readme.md. Interesting. Now, we should read it carefully again. This time, I found the file 332703 says it contains a tree named 856072, and the tree tells that there's a blob named 04748b in it, and the content of the file 04748b is what we wrote in the readme.md on the working directory. Yes, I believe you are smart enough to find out that it should not be the coincidence. I encourage you that now you can try making a new repository and make any new files on the working directory, then commit it into the repository. Use the command I show you to see the relationship between all those files. We seem to have some clues about the repository, but the file name is still strange to us. Now let me introduce the concepts of blob and SHA1 in the next section. We already found that the strange code is actually the name of the files saved in repository. These files are the so-called blob. We will mention it later. Also, don't worry about the tree commit. They are nothing but the Git object type and are saved as blob in the repository. Currently, just keep in mind that besides the history files, Git also manages these object type files in the repository. And that's why you can see them in object folders. Back to the SHA1 topic, we also find that the files are saved under a directory named by 2 hexadecimal digits, and the files themselves are named by 38 hexadecimal digits. Actually, the folder name and the file name plus together is the real SHA1 code for the file. And that's why when we use catfile command, we send it the folder name plus file name as the parameter. Then why we separate the SHA1 code by the first byte of the 20 bytes hash? This is to improve file system efficiency. Imagine if you put too many files in the same directory. To search a certain file is like search in a flat list. We use the first byte as an index. This could be faster when searching a file, just like using a hash map. So logically, the repository file system is flat. The only folder it creates is for improving the efficiency. Before peering at the contents of the tree object in more detail, let's check out an important feature of SHA1 hashes. We use git write tree to check the tree in index. Now do it again. Every time you compute another tree object for the same index, the SHA-1 hash remains exactly the same. Git doesn't need to recreate a new tree object. In this sense, the hash function is a true function in the mathematical sense. For a given input, it always produces the same output. With the 40 hexadecimal digits, you have 2 to the power of 160 possible SHA-1 hashes. That number is just incomprehensibly huge. Even if you hired a trillion people to produce a trillion new unique blobs per second for a trillion years, you would still only have about 10 to the power of 43 blobs. Thus, it's almost impossible that SHA-1 will meet collision. When I mention the collision, it means two different objects produced the same hash. That's extremely important. For example, if you create the exactly same content as another developer, regardless of where or when or how both of you work, an identical hash is proof enough that the full content is identical too. In fact, Git treats them as identical. From this perspective, it is easy to tell whether two files are identical. You can have a try on your machine. Even if you change only one byte of the file, the SHA-1 hash Git computes will be totally different. Now, modify our README file and add the file to the repository. Try writing a tree. This time, we found that the tree is different from the last one. Continue check the tree 36DA20 and then check the blob 08BD96 referred in the tree. We found that the content is the same as the latest readme.md in our working directory. Blobs. Each version of a file is represented as a blob. Blob, a contraction of binary large object, is a term that's commonly used in computing to refer to some variable or file that can contain any data and whose internal structure is ignored by the program. A blob is treated as being opaque. A blob holds a file's data but does not contain any metadata about the file or even its name. So blob is the basic unit saved in Git repository. Each version of a file is saved into the repository as a blob. The repository also saves Git object type such as tag, commit, and tree. Git repository never saves duplicated files in it. You won't find two identical files in a repository. We will make an example later. Let's take a close look at the blob. We have those files in objects folder. They're actually the blobs we've talked before. Using the cat file-p command, we are able to check the content of each blob. We actually have repeated this operation so many times. I know it's kind of boring, but I'm sure that I will use the command even more frequently later. However, it is a way to leave us a deep impression on the structure of the repository. As long as you fully understand the principle, actually, you will nearly use the low-level command when really working with Git. Okay, through the command line, we can see that we have a commit and tree and history files in the repository. Here, we can find the first version of readme.md and the second version of readme.md we just modified. All of them, I mean the commit, the tree, and the history files, are saved as blobs in the repository. Now, let's take a further step to see the relationship between Git repository and working directory. Simply copy the readme.md into CMake folder and code folder. Here on the right bottom of the screen, we list our files in working directory. We have a root working directory folder named Maya, and under the working directory, we have readme.md, a CMake folder, and a code folder. Under the CMake folder is the CMake copy readme.md, which we copied from readme.md just now, and the same to the code copy readme.md on the code folder. The three readme files are identical, although their file names are different. Now let's turn to the Git repository. First, we add the modified files into the repository, and then write a tree. Here, we get a tree object in the repository, and let's check its content. We would like to represent the file status on the working directory according to the description by this tree in the repository. Cat file-p. Carefully read the content. It says we have a file saved as blob in the repository. The file's name in the repository is 08bd96, and its name on the working directory is readme.md. The content of the file could be retrieved from this blob. Besides, we have a tree object saved as blob in the repository. The tree's name in the repository is f87863, and the corresponding directory name on the working directory is CMake. The same way to pass tree 1d626b. Continue check the content of the two tree. We can find that there is a file named code copy readme.md under the tree, as the tree represents code directory on the working directory. So here it means we have a file code copy readme.md under Maya-code folder, and the content of the file could be retrieved from the blob 08bd96 in Git repository. And the same to the tree 1d626b. Remember we mentioned that we don't have duplicate files in the repository? Although the three files under the working directory have different file names, as the content are the same, they refer to the same blob 08bd96 under the Git repository, and their different file names are described by the tree object. This is a good property, since even we have thousands identical files under the working directory, we only need one blob in the repository to refer to them. Well, we still need to insist a moment before we have a break. If you have already understood the concepts we've talked, then the journey from now on will be easy. Let's now talk about the commits. We actually have mentioned the commit several times before. Now let's go into some details. A commit object holds metadata for each change introduced into the repository, including the author, committer, commit date, and log message. Each commit points to a tree object that captures, in one complete snapshot, the state of the repository at the time the commit was performed. The initial commit, or root commit, has no parent. Most commits have one commit parent. Some have more than one. For example, a merged commit may have two parents. You can use cat file-p to check the content of a commit. As we've talked just now, we can find the tree, the author, and commit message in a commit. And I believe you can find that with a commit, we can represent all the files of a version on the working directory. Trees. A tree object represents one level of directory information. It records blob identifiers, path names, and a bit of metadata for all the files in one directory. It can also recursively reference other subtree objects, and thus build a complete hierarchy of files and subdirectories. We have mentioned the trees so many times in today's talk, and actually I guess you already know very well of it. Yet let us again make an example to review our knowledge. Assume there's a commit 84784A. In it, we have a root tree 45AD5F. Check the tree. There's a file named readme.md under the working directory root folder, and the file's content could be represented by the blob d62 d6f in the Git repository. Besides, we have a subtree 2a338b. The blob saved in the repository represented the subfolder under the working directory root folder. Check the blob 2a338b. We have two files whose name under the subfolder are readme.md and readme-copy.md. Both files refer to a same blob 76097E in the repository. Although they have different names, their contents are identical. Now, let's describe the working directory by the commit. We have a working directory root folder. In it, we have a readme.md file. Besides, we have a subfolder. In it, we have a file named readme.md and a file named readme-copy.md, and they have the same content. With all these concepts we've talked, it's time to summarize. Git is a version control system. It uses commits to describe history files. A single commit represents a version. With the commit, we can represent all the file stages on working directory. Let's review the knowledge by the following practice. Before continue, I have to apologize for illustrating like a voice repeater. Actually, I just want to emphasize the structure of the Git file system. So anyway, let's begin. Change the readme file on root working directory. Make a commit. Write down the second commit as the message. Using git log to track history information. The log told us we have two versions in all. The latest version is saved in a blob named 1dc13e in the Git repository. The former one is saved in a blob f9f155. Continue, check the first commit. By the description, we find the commit has a parent commit f9f155, which is the former commit showed by the log information. Sounds good. It is consistent with our thinking. Go back to the latest commit. There's a root tree 316582 in the repository, and it represents the root working directory. In this tree, we find a file named readme.md, whose content could be represented by the blob 75fc82 saved in the repository. Besides, we have a subtree f87863, which represents the CMake folder under the root working directory. And we have a subtree 1d626b, which represents the code folder under the root working directory. Further check the two trees. There's a file named cmake-copy-readme.md under CMake folder, and its content could be represented by the blob 08bd96 in the Git repository. There's a file named code-copy-readme.md under code folder, and its content could be represented by the blob 08bd96 in the Git repository. Since the two files refers to the same blob, they have the identical content regardless of their file names. I think you should now be able to draw the hierarchy of working directory by the description in a commit. The same way to check the parent commit. There's no parent commit in it since it's the root commit or the first commit. The messages: add new files. There's also date information in it. A little episode. I worked on a different computer to record the video today, and the first commit SHA1 code, F9F155, is different from the SHA1 code 332703 I recorded in the very beginning. You can go back to check the 8th slide. The reason is simply because the time I edited those files was different. Thus, the SHA1 code Git computes was also different. However, as the content of the files are the same, so the SHA1 code of the trees do not change. Okay, back to our commit. We find a readme.md on the root working directory, and its content could be represented by a blob named 04748b saved in the Git repository. Forgive me being so verbose, but this part is really quite important. And I think it's the very basic core knowledge for us to understand how Git works. If you fully understand what we've talked just now, please continue to the next chapter. We will introduce the concept of index and talk about the basic workflow when using Git. Thank you for listening. See you.